Welcome to this short tutorial on Bratu problem. Although this is your assignment problem, I'm just going to walk you through this model. So in the parameters I have listed here epsilon, which is 0.5, and I am simulating the case for mu is equal to 0. C is the constant you need for estimating or calculating your analytical solutions. And then we have talked about in the previous tutorial that the equation structure resembles the heat equation. So if I just click this, you can see the equation dA is 0 and the source term is packed into the coefficient F, and C is 1, and also the geometry is defined as an interval from -1 to 1, and other than that I have just added a global ODE here just to calculate C, which is required for analytical solution, and the mesh size we can control by using this size feature here. So right now I have a maximum element size of 0.05, which means our total number of mesh elements, you can always look at by clicking statistics, is 40. So this is the model, and initial value I have given for the state variable u, and I have specified the boundary conditions, which is 0 at both of these endpoints. Okay, so and with this, if I compute the solution, so what I'm plotting in this 1D plot group is two quantities. One is the state variable, which is calculated by this simulation, and second I'm plotting an expression u underscore ANA, which is the analytical solution, which I have declared in the variable here. So in the variables I have declared this expression, which is the analytical solution for mu is equal to 0 case, in terms of the variable C. Okay, so these two quantities are plotted, and you can see that the analytical solution matches well with the numerical solution. Now we know this problem has multiple solutions for any given value of epsilon. So if I just say go to initial values and change, say, my initial guess for as making it 2 from 0, and then I recalculate, then you'll see a different solution. So numerical solution is the blue curve and the analytical solution is the red curve. Now the difference is the numerical simulation is converging at the second solution, the other solution for the same epsilon value. Okay, so and the analytical solution is still calculated using the C value, and again this parameter C is calculated using this ODE. So what we can do is we can also change this initial value, which is calculating C, and so if I make this change as 2 and recompute, then you're going to see now both the analytical solution and the numerical solution are converging to the other solution. So some of you have asked that you see a difference in the analytical solution and numerical solution calculated from COMSOL. So most likely it is that you are plotting two different solutions for a given epsilon value. So by changing initial guess, you can change the solution. Okay, so that part we have seen. Now the other questions was to calculate the norm. Okay, so the MATLAB calculate the square root of sum of squares of a state variable at each node point. So similar thing you can to do that, you can just click on the derived values, right click, and select this in the integration, select line integration, and in line integration you need to add all domain, this complete domain. And now there are two settings here if you see the integration settings. So one is this integration and other is summation, and both are related. So now since the MATLAB norm is related to the summation over each of the node points, so you just select summation here, and in the expression you can write u square, and you can just compute this. So if you compute, you will see so this is the summation of u square at all the nodes value, but for norm you need to take the square root. So you can calculate the square root of this number, but if you going to compare it with your MATLAB number, then this value will be higher, and the reason being the reason being the different number of nodes. Okay, so you have to make sure the number of nodes you use in MATLAB and in COMSOL are same. So so there is a little bit of trick here. If you go here and click on the discretization and check here, so here element order is quadratic, which means a subnode is placed between each element. So effectively, to make number of nodes equal in your MATLAB and COMSOL simulation, either you need to select linear here and then give equal number of nodes in COMSOL and MATLAB, or if you are selecting quadratic here, then you have to give half the number of nodes in COMSOL as compared to MATLAB. So if I select linear here and do my calculation, say if I recompute and then if I compute my line integration again, say in the same table, you see your the same value is now reduced because now you have chosen the linear discretization. So now this value which we have solved using calculated using the linear element, it should match your MATLAB norm exactly for the same number of nodes. Okay, so I hope this is clear, and if you want to calculate for many different values of epsilon, you just need to run the parametric continuation and calculate the norm for all the epsilon values. Okay, so if you have any other questions, please write to me or Dr. Kumar, and I hope it is clear. Before ending it, let me also just quickly go over this other operators here. So you can similarly how we used integration, we can calculate use this averaging operator or maximum or minimum operator, and that will find you the minimum value of your state variable or the maximum value or the overall average value for the line average or for a surface. So you can use any of these depending upon what you need. Okay, so with this I'll close this. Thank you for your time.